Ladies and gentlemen, Johann.
Good morning, everyone. So DAOS stands for Distributed Application Object Storage, and it's actually misnamed because we don't expect application to run directly on top of DAOS. It's actually a building block of the exascale storage stack that we are building. So we work on DAOS as part of the Fast Forward research project. So I want to emphasize that this is a research project, and at this point, DAOS implementation is a prototype. So don't be afraid by all the changes we are going to present. So Liang will start by presenting the DAOS API, which include the container, the shard, and object API. And then I will present the epoch API as well as all the Lustre changes. Liang.
So DAOS, as Johann said, is a part of the DOE Fast Forward IO project, and we hope it can be the evolution of Lustre for exascale computing. And briefly, DAOS is a scalable, transactional, global shared, distributed object storage system, all fancy words together. And we need to, it requires to change many Lustre components to provide a whole set of new IO system calls. These APIs should be totally asynchronous and to provide high concurrency, and they can support transaction and can support collective operations. So before diving into APIs, we should introduce a few concepts here. DAOS container. DAOS container is an object or address space which is partitioned over many storage targets. Each partition is, which partition we call the container shard, is actually a virtual storage target. And externally, a container is a new file type in POSIX address space, and user can see only one entity for a container in POSIX namespace. But internally, a container can contain tens or hundreds of shards, and each shard can contain millions or billions of DAOS objects. So container and object inside container is really the place that application can store its data and metadata. And in current phase, container is the entity that user can start transaction for. This graph shows that how we are going to implement container in Lustre. Actually, it's quite like the way how we implement a regular file. The inode MDT is the place that we store the layout information of a container. And the difference with the regular file is for a regular file, the layout is really where we store data objects, and for DAOS container, the layout is about where container shards lives in. And each shard is kind of sub-volume that can contain any number of DAOS objects. These are major APIs we provide for container operations. The first is DAOS container open. User can provide a path in POSIX namespace, and then this function will open or open create a container. This function will, on completion of this function, it will return a handle. The handle is just like a file descriptor. User will use this handle for following I/O requests, and also user needs to provide a access mode, which is quite like the access permission of POSIX. And also user can indicate it's a collective or open. I will introduce this in the next page. Container close. It's straightforward. It just release the open handle returned by container open, and the container unlink it's just like POSIX unlink. It will destroy container and destroy all shards inside the container. Container query will return the major attributes of container. For example, how many shards inside this container, or which shards are disabled, and what's the latest epoch number of this container. Epoch here means for writer, epoch is a transaction ID. For reader, epoch is a snapshot ID. Johann will introduce this later. And this graph shows how collective open works. First, when a user do container open, he needs to indicate that he wants to share this open handle with many other processes. After the completion of the open operation, he call another function, DAOS local to global on the returned open handle of the container, and this function will convert the local handle to a global handle. What's inside this global handle is really our layout information of this container and capacities to enforce securities. The process did open will send this global handle to peer processes or any communication library, for example, via MPI. After other processes got this global handle, he can call another function, DAOS global to local. It will convert the global information into a local handle. Then they can start to use this local handle for I/O operations. All processes share this open handle share a collective open can have the same access permission to the container, and if the master opener, I mean the process did the real open, close the open handle, the capacities will be revoked. These are shard operations. All shard operations will require a container open handle as input parameters. The first one, shard add. It requires user to provide placement information of a storage target. For example, in which rack, which node was the target ID, and this function will create a new shard inside that storage target and add it to the container, and it will return a logic ID. I mean, it's just an integer and it should be unique inside the container. Shard disable, it will disable any number of shards. Any number of shards in the container. User just need to provide an array of shards IDs. And oh, by the way, the first function, shard add, it can also take an array of placement information of storage target. So he can add many shards in one call. And list object will list all objects inside a shard. And query will return the information of storage target and the space information and the number of objects and, for example, health status of storage target. DAOS object lives inside the container shard, and it can be identified by object ID. Object ID, high bits of object ID can address a single shard inside a container, and low bits of object ID can address a single object inside a shard. A DAOS object is really a byte array, and the user can read, write, overwrite arbitrary number of bytes from any offsite, and we always assume that all objects exist, which means in the backend file system, the object is created on the first write, and it will be removed and recycle all space on the object punch from 0 to infinity. And if user is reading from an empty object or from a non-existent extent of object, or it just gets all zeros. Also, DAOS will not maintain any metadata information for object, which means we can avoid overhead if user does not really require it. So it's operator's responsibility to maintain metadata information. For example, they can just store the metadata information in reserved bytes of object, or they can store metadata information in an index object, which is just an object with famous shard ID and a famous object ID, for example, 00. Before user can use an object for I/O operations, they need to open the object. And the first thing they need to provide is a container handle, then the object ID, so they can identify which object. And also, user can hint the I/O pattern, so DAOS knows how to catch, how this object is going to be locally cached. All these object read and write, they are quite straightforward. They just the way user can submit the I/O request, and the user also need to provide a transaction ID, I mean epoch. And all these operations are asynchronous, so the completion of these operations are are notified by event, and the user can get this event by polling on event queue. Event queue is another component of DAOS. Really, this is the time I can take for this, and Johann will take over complex things.
So I'm sorry, it seems that the top of the slide is truncated, so I don't know whether I can just present it like this, maybe cleaner. So the epoch API is an epoch number is really a transaction identifier which has to be passed through every single DAOS IO operation. So the actual number is decided by the DAOS user, the application, the middleware. However, there are rules. You can only read from the past, so from already committed epoch, and you can only write into the future to uncommitted epoch. The scope of an epoch is currently limited to a container. It means that a transaction runs on all the shards of the container, which are transactionally updated on commit. However, in the future, we might want the epoch scope to be more flexible and to allow an epoch scope to span multiple containers and maybe even to span multiple subset of containers. So write can be submitted to any epoch into the future, any epoch which are not yet committed, and they are effectively logged on the OST into what we call an intent log. So we log the operation and the data into the intent log. But then it's still committed in order. So there is an explicit call from the DAOS user, which is called DAOS epoch commit. So you specify an epoch that you want to commit, and it's actually cumulative. You will commit all epoch up to the epoch passed to the DAOS epoch commit call. There is the notion of highest committed epoch, as Liang already mentioned. The epoch scope not only comes from the write capability, you can also read from already committed epoch, so it comes from a read cursor, which can effectively be moved to the highest committed epoch through a special call DAOS epoch slip. The MDS tracks all reference from epoch scope opener, and once a reference of the old epoch drops to 0, then it releases the whole snapshot. So here is the traditional flow of a DAOS operation. So the epoch scope is opened by the client. We have a new feature in Fast Forward called server collectives. So it allows us to send messages to a set of nodes in a more very efficient manner through a spanning tree. So the MDS at this point will propagate the capability associated with the epoch scope to all the shards and also fetch the HCE. Then the client can submit IO, wait for completion, and then commit the epoch. It means that it is done with this epoch number, and it wants it to become persistent on the backend storage. On epoch commit, the MDS, which tracks all openers, when it gets commit for every epoch scope opener, it notifies the MDS and propagate the commit message to all the OSTs, all the shards, which will create a snapshot on disk. Then the client can close the epoch, and it's done. So all are shard and container represented in Lustre. So a container is actually a regular file on the MDT. It has an MDT feed and also a special layout. This layout is quite different from the LOVEA because there is no striping. It's just a list of shards. So each shard is assigned a unique sequence in the Lustre feed sense. So the layout is actually a list of sequence plus a status to know whether or not the shard was disabled. This layout is replicated on all the shard, so there is a copy on all the shard of the container, and the shard also maintain a private object index, OI, which point at all the local objects maintained by this shard. So how is a shard represented on disk? So initially we considered Btrfs, but we finally decided to go with ZFS, mostly because it's more mature, and also because we also have a ZFS OSD. So a shard is represented on disk through multiple data set and intent logs. So we have, as I said, one intent log per epoch to be committed, and then a staging data set where the next commit is prepared. So we take the intent log and we flatten it into the staging data set. So we actually parse the intent log and re-execute all operation on the staging data set. Data is moved efficiently through a block remapping scheme. And then there is also a set of snapshots for readers, which are written by readers, and once the reader who drops the reference, we release the snapshot. All this framework will be built through extension to the OSD API and with a shared aware OFD. So DAOS also comes with a lot of changes on the client side. So the DAOS IO pass is actually more straightforward than the CLIO POSIX client, because there is no locking and no striping, so we don't need the CLIO complexity, and we will just build a new module called DCL, DAOS client, which sits directly on top of OSC and export OSC object through the DAOS library. We also have to make several changes to the metadata layers, LMV, MDC, in order to handle the container and epoch protocol. The DAOS API is totally event-based, asynchronous, so it means that all operations are non-blocking. So you go into the kernel, we queue RPC to portal RPCD, and we return straight away. Then on completion, portal RPCD will call a callback through the stacks, which will update the event at the top of the stack. And the application then can poll the event queue and get completion of event. We are not going to use POSIX IO because we look at it and it's not generic enough, unfortunately. So we will come up with our own event and event queue implementation. That's all. Thank you.
Questions? All right.
Hi, is it possible to, do you support an object append operation? Or is it just read and write?
As far as the object is concerned, is only truncate, read, write.
Okay.
Bunch, actually. Bunch.
Are shards, can you break up shards and make them multiply themselves, each one? Say if you have one shard, can you make it into 4 shards? Can you splinter it?
No, you will actually create a new shard. This is the scheme. You cannot subdivide a shard into additional shard. It's a data set in the ZFS way or ButterFS way, so it cannot be subdivided.
So you guys were making these changes to Lustre in order to support the new code. How much of this is of general use to all of Lustre, not necessarily specific to the Fast Forward project?
So there are some parts like the server collectives and the health network that can be built on top of it, which can be used by the Lustre POSIX client, definitely. But then there are also some container representation and so on, which are very specific to DAOS. So I think the server collectives and the spanning tree to have scalable communication is a good example of a feature that might benefit from the today's Lustre.
Johann, can you talk a bit about how perhaps when somebody creates a shard, they can tune it for different types of workloads, you know, streaming versus IOPS, and maybe a bit about how that's implemented?
Yes, so there is through the DAOS API, we export a lot of information about the target, so the type typically, so it's whether it's a rotating disk, it's SSD, and so on. So there is a whole set of information which is exported to the DAOS user. And based on that, the DAOS user can can make more efficient placement and allocation based on the features that are exported through the storage tree topology. So we also provide the mapping between node, site, rack, and so on, which is exported to the application to handle a more efficient placement. And then when you open the object, you can also specify the type of operation you are going to make, whether it will be sequential I/O, streaming I/O, random I/O, and so on. And based on that, Lustre will have a different approach with regard to your RPC. So for instance, for random read, we will definitely not perform any read ahead. For streaming I/O, we will do aggressive read ahead. So we have a lot of logic inside the code where the application can actually claim how it is going to use the object, and Lustre will adapt based on this.
And Eric's talk will be more about high availability.
Yes, I think so.
John, did you correctly understand this DAOs should be don't have a LDLM logs to protect?
Exactly.
So it is will be lockless IO only.
Yeah, it's real lockless I/O,
Without
unlike
any cache
today's lockless I/O.
coherency and other protections for caches on clients.
So actually, it's the cache becomes epoch aware. So your cache is not tagged with an epoch number. So you can only cache anything from a given epoch because this is committed data. And now the issue is how you move your cache from one epoch number to the new one to find out exactly what was changed into your cache.
But if one client read some data already from past time epoch, but
You cannot
new
modify the
client,
past.
Will be right and create a new epoch. So how client cache will be invalidated and flushed?
So when the client, so it's always safe to cache data for a given epoch, right? So because the past cannot change. And then for future epoch, when the reader moves his read cursor to a new epoch, it will revalidate the cache on a per object basis. So we will throw away the whole cache for the object or just keep everything if the object was not modified at all. And then we're also considering some sort of, in the future, obviously, deduplication implementation, which will allow us to share pages between different representation of the cache on a per epoch number.
I ask about difference. So some network commits coordinator should be notified a client about new epoch on such object created or not. So if you have a reading and past epoch, but new epoch created, you should be have something to notify client new epoch for this object is exist. Correct?
I'm not sure to understand the question, sorry.
Well, client read some data in past epoch, but different client write new data and create a new epoch.
So there is only one writer.
It is create a distributed transaction, and this transaction manager should be notified first client to flush and invalidate one.
So there is just one writer, the container can be opened for write just once. There cannot be multiple writers. Multiple writers have to be in the context of the same application. So we don't have such a problem, I think.
Sorry, we've got